We are now in chapter 13, where we're going to look at how skin is treated with antioxidants, and we'll discuss this from two aspects. Basically, from a formulation strategy, what are some of the things that we need to consider in order to formulate antioxidants, and then we'll also look at the various antioxidants that are used in the formulation but intended to be delivered to the skin. So you really have two categories here. You have antioxidants that are used in the formulation, and that is to prevent the formulation from oxidizing or undergoing lipid peroxidation, for example. And then you have antioxidants that are in the formulation but are designed to be delivered to the skin, where they can act as antioxidants in the skin itself. So in terms of the formulation strategies, you want to make sure that you use the correct form of the antioxidant, and that could be anything from you want to consider pH effects, if the antioxidant is going to have a charge or not at certain pHs or pH levels. You also want to ensure that you use the correct form of the antioxidant in terms of, some antioxidants aren't stable in products. For example, there's a lot of issues, or there has been historically, with formulating vitamin C and even vitamin E or alpha tocopherol. And for this reason, many sort of analogs of those antioxidants appeared in the marketplace. And what you want to ensure is that whatever that analog is, or that sort of mimic antioxidant that has very similar structure to the original antioxidant, but it might be slightly different and it might not function exactly the same way as the original antioxidant. So you really want to consider that. You also want to have a decent shelf life for the product so that the antioxidant retains its activity when it's finally delivered to the skin. You don't want the antioxidant to become oxidized when the intention is to deliver that antioxidant to skin for a cosmeceutical application. You also want the antioxidant to be an effective transcutaneous absorption agent, which delivers to both epidermis and preferably even to the dermis. So when we choose an antioxidant, we can basically choose it based on its mechanism of action. So you could have, these different groups here that are shown on this slide: radical and oxidant scavenging type antioxidants. These would go after reactive oxygen species and reactive nitrogen species. You may want to choose something that's a metal chelating agent that chelates iron, copper, for example. If you recall from previous chapters, we discussed the Fenton reaction and some other reactions involving these metal ions. If you're able to chelate those, sometimes you can prevent oxidative reactions from occurring. You may also choose an antioxidant that inhibits redox-sensitive transcription factors. Two examples of those are nuclear factor kappa beta and activator protein 1, also known as AP1. These can cause oxidative type reactions in the body and also in the skin, and preventing their action could be a way for an antioxidant to function in this respect. You could also choose an antioxidant that inhibits pro-oxidant enzymes, and this is another category that we won't really discuss any more than what we're talking about on this slide. But just for your information, there are ways to go about that. So there are general ways to sort of look at antioxidants and understand or know what type of efficacy they're going to have, just from an in vitro perspective. When you start to talk about in vivo, the situation becomes much more complex because then you're looking at the migration of oxidants or reactive oxygen species and also of the antioxidant. Where does it migrate to? Where is it delivered to? But if you just look at the standard reduction potential, you can just get an idea of how efficacious an antioxidant is itself in some type of solution. And what we see is that ascorbate has the lowest on this list, 280 millivolts. That's followed by alpha tocopherol, which is 480. And these aren't really that low, but they're lower on this list that we have going on here. Glutathione is actually significantly higher than those, the ascorbic acid and alpha tocopherol. And then if you look at these materials, epigallocatechin gallate and epigallocatechin, epicatechin, and epicatechin gallate, these are all tea polyphenols. So these are ingredients that are found in green tea, and they're all very high in terms of their reduction potential. And that would explain why green tea is infamous for its antioxidant potential and benefits for good health. Tea flavin and tea flavin digallate, these are from actually black tea. These are also really high in terms of their reduction potentials as well. So in general, the idea is that you could look at a chart like this and you could more or less have an idea of how strong of an antioxidant you were dealing with. I mentioned already that formulations oftentimes are preserved with antioxidants, and this is to prevent oxidation of the formula in the package. It could also be to prevent oxidation of an antioxidant that is in the formula with the intention to deliver it to the skin as a cosmeceutical agent. So these are antioxidants that are commonly used in formulations and historically, and they still are today. Probably the most common is butylated hydroxytoluene. This has the structure that you can see here where you have a methyl group at the para position to the hydroxyl group, and then you have two terp-butyl groups in the ortho and meta positions on this ring. The OH bond here is the key to the antioxidant activity of this molecule. Essentially, this hydrogen or proton is donated to a free radical species, and that's what essentially neutralizes the free radical species. You're left with a free radical butylated hydroxytoluene species. However, what we have to keep in mind is this is actually a stable free radical species, so it doesn't have the high reactivity that other free radicals would have. We also have butylated hydroxyanisole, whose structure is shown here. The tertiary, essentially you have a hydroxyl group, and then at the para position you have a methoxy group, and then at any one of the other positions along the ring you could have this terp-butyl structure as indicated here. We also have tertiary butyl hydroquinone, whose structure is given here with two hydroxyl groups and one tertiary butyl group. In this case, a proton can be given by either either up here in this OH or in the para position as well. So those were for the formulation. Now just looking for the treatment of skin. So as a cosmeceutical, which antioxidants are effective? You can look in your textbook in chapter 8, and there's really a nice review of all the different antioxidants that work well in terms of being delivered to the skin, and they have cosmeceutical efficacy. However, this is just a summary of some of them that are really well known, and there's been a lot of research that has repeatedly shown that these antioxidants are efficacious. Starting first and foremost with ascorbic acid and vitamin E. A lot of work has been done with these two, and for treating the skin, they have been shown to really do a lot of good. Selenium is also very good. In addition to that, glutathione and also alpha-lipoic acid, both of these, as well as the T polyphenols that we already mentioned, the epicatechins. And in addition to that, soy isoflavones and Silymarin also are efficacious in treating the skin. We'll talk about a few of these individually, starting with ascorbic acid, essentially listing the benefits and the caveats of this particular molecule. In terms of the benefits, ascorbic acid neutralizes reactive oxygen species. It protects against both UVA and UVB. In addition to acting as an antioxidant, it also stimulates collagen synthesis. It prevents UV-induced immune suppression. It alleviates inflammation. It decreases UV-induced pigmentation, enhances surface moisturization, and even increases skin barrier function. So there's a lot of different benefits for ascorbic acid, and the principal caveat is that it's unstable in formulations. So to try to circumvent the instability of ascorbic acid, the structure of ascorbic acid is shown here. These other molecules have been designed by different manufacturers of specialty ingredients in order to have the ascorbic acid structure, but to introduce some type of functionality into the molecule to make it more stable. And here's an example where you can see this aminopropyl ascorbyl phosphate. You have this phosphate group, and then you have basically a 3-carbon chain with an amino group that's shown here. In another example, which is actually really common, you have magnesium ascorbyl phosphate, where you have, up in this section, you have the phosphate group added, and then you can see, so this is where you would have one of the OH groups originally, and then up here you have, this is upside down, but this is essentially, this top part is the same structure that you see in ascorbic acid here. Sodium ascorbate, you can see, has the OH group, and then on this side it has a sodium and oxygen atom attached. The rest of the molecule is the same. Sodium ascorbyl phosphate, again, the top part is the same, this is just upside down, and then you have a phosphate group here, and then you would have a sodium counterions to this negative charge. I forgot to mention, up in this one you have magnesium ions that basically are the counterion for this negatively charged oxygen. So if we go to the tocopherols, there are many benefits, so many that I didn't even list them here. Similar to vitamin C, it has just many different benefits in skin, many different studies over the years. The main caveats of the tocopherols is that, again, like vitamin C, they're unstable in formulations, and also they can cause contact dermatitis, so they can cause some type of some inflammation in the skin. So to sort of circumvent the instability of tocopherol or alpha tocopherol, a number of different derivatives have been made over the years. This is showing you the tocopherol molecule here. Essentially, this is pretty much what you find in alpha tocopherol. It's written a little bit differently than the one that I introduced to you, but it's essentially the same molecule. One of the principal molecules that has been made to replace tocopherol, or to sort of stand in its place, is this one, tocopherol acetate, which is essentially the same molecule, except up in this, instead of having a hydroxy position here, you have this acetate group. And what's there's some conflicting research in the literature that shows that some studies show that when this molecule is applied to the skin, this acetate group is cleaved off, and then the remaining oxygen is actually protonated, so you end up with alpha tocopherol in the skin. Other studies have showed that that doesn't occur, so there's probably about 50% of the studies show that it does occur, 50% of the studies show that it has not, or it does not occur. So that's still up for debate in the literature. And again, please note that this is kind of reversed, but this up here would normally be where you would have the hydroxyl group drawn for the tocopherol. We also have Trolox, which is the water-soluble version of alpha tocopherol. And essentially, the chromanol ring portion that's here, this is all the same as alpha tocopherol. The main difference is that you have a carboxylic acid group instead of a long phytyl chain that's shown here. So this makes this soluble in water, which offers you a lot of different flexibility, especially in formulating with it. Another molecule is dimethyl methoxychromanol. You can see this has similar structure, a little bit different. You have a methoxy group here. You have the OH group that's shown here. And again, this one's sort of reversed. Normally we're used to seeing the OH group up in this corner, but it's reversed in this case. And then this is where you would normally have the long phytyl chain, but in this case you just have two methyl groups. Alpha-lipoic acid is also a very important antioxidant for treating the skin. Here we can see its structure, where you have this disulfide bond in it, along with this sort of, not that long, but an alkyl chain that ends with a carboxylic acid group. When this undergoes oxidation, the disulfide bond is cleaved, and essentially you're left with dihydrolipoic acid. So you go from alpha lipoic acid to dihydrolipoic acid. But the beauty of this antioxidant is that you can see benefits and activity in both the oxidized and reduced forms. And this over here on the right is just a summary of the benefits of lipoic acid and dihydrolipoic acid. So in terms of antioxidant behavior, lipoic acid only gets a 1+, but it gets a plus, which means it works and functions as an antioxidant. But dihydrolipoic acid gets 2 pluses, so it's even better, or has greater activity in terms of being an antioxidant. Scavengers of reactive oxygen species, we see that both lipoic acid and dihydrolipoic acid can scavenge reactive oxygen species. For metal chelation, we only see that with the lipoic acid form. We do not see it with dihydrolipoic acid. Interacting with cadmium, we do not see it with lipoic acid, but we do see it with dihydrolipoic acid. So again, cadmium, of course, would be dangerous and could cause sort of negative interactions in the skin. It's not something that you would want to have there. And then we look at the regeneration of other antioxidants such as vitamin E, vitamin C, glutathione, and ubiquinol. And we see that lipoic acid doesn't regenerate antioxidants, but dihydrolipoic acid does in fact regenerate antioxidants. And dihydrolipoic acid also repairs damaged proteins. But one thing that we should also note is they both have some pro-oxidant behavior. And that's common with many different antioxidants, is when used in excess, they can actually become pro-oxidant in terms of their behavior. Let's talk a little bit about polyphenols. And polyphenols are a class of compounds that are found in leaves, berries, tea, beer, wine, olive oil, cocoa, walnuts, peanuts, all types of nuts. Yerba mate, that's kind of like a tea drink from South America. Pomegranate, persimmons, all different fruits. We're just naming a few here. But we find these polyphenols present, and the polyphenols, they often give these sort of nice rich colors to the fruits that you see. And we could break them down into these different classes. That you could even go further and break them down into more classes, but to keep it simple, we'll break them down into these 5 classes consisting of phenolic acids, and these are used in formulation quite a bit in skincare, consisting of ferulic acid, caffeic acid, and rosmarinic acid. Then you also have the flavonoids group, and 2 common ones there are quercetin, which is pretty well-known, well-used antioxidant, and then of course the epicatechins, which again, these are the green tea antioxidants. You also have lignins, and then tannins. If you remember, tannins are antioxidants that are found in beer. One tannin that's important is gallic acid. And then we have steel beans. And overall, the steel beans may not be that commonly used, or maybe not that important, but there's one steel bean that is very important, and that is resveratrol. And this is actually found in certain red wines, and it's the compound that you always hear about, the French paradox, where the French have, in a certain region of France, the people have a very high diet in fat intake. They eat a lot of pâté, foie gras, things like that, and but they have very low cholesterol levels and low sort of coronary disease and things like that. And it's believed that it's due to the consumption of wine by this group of people, with the wine containing this sort of interesting compound known as resveratrol. So structurally, these are just some flavonoid type structures. We have flavone, flavanone, and isoflavone, and you can see the differences in terms of just how these are arranged. We have the A, B, and C ring in each case, with A being on the left, B on the right, C in the middle. You can see that the C ring is almost the same in all cases, except in flavone, in isoflavone, you have a double bond on the right side. The difference between these two is that the B ring is actually up in the number 2 position here, and it's in the 3 position in the isoflavone molecule. But otherwise, the molecules are the same. The flavanone, as you can see, does not have the double bond, but does have the ring sort of sequence similar to that of flavone. So it just differs in the double bond. And essentially, these A and B rings, it's not shown here, but these actually have multiple hydroxyl groups coming off of these rings. And these hydroxyl groups are able to donate the hydrogen atom, and that's what gives these molecules their antioxidant property. The tea polyphenols, as we already mentioned, a little bit about green tea, but all teas actually come from the same plant known as Camellia sinensis, and the difference between the teas is actually the way that they're processed. Green tea is the least processed, and that's probably why it has such efficient antioxidant behavior. Oolong tea and black tea actually is the one that's processed the longest. But regardless, you can find antioxidant species in all 3 types of teas. These again are the major polyphenols in green tea. These are the epicatechins, which you can see, similar to the structure that you saw for the flavone type molecules, you can see that you have a similar type structure here with epicatechin. Epigallocatechin, you can see there's certainly some differences between it and epicatechin, but they have a sort of similar structural motif. The difference primarily being with the hydroxyl groups that are attached. I believe the epigallocatechin has a hydroxyl group here where I'm circling, whereas the epicatechin does not. And then you also have epicatechin 3-guaiate. The 3-guaiate, you can see you essentially have this large portion or pendant group that's attached to the main structure of the flavone that's shown here. Epigallocatechin 3-guaiate is basically similar. Again, the main difference would be this hydroxyl group is located here. It's not located in the one up above. We also have the polyphenols that are found in black tea. T-flavin and T-rubigin are the two principal polyphenols that are found in black tea. The soy isoflavones are another important class of polyphenols, and one that's particularly useful and there's been quite a bit of interest around in skincare is genistein, whose molecular structure is shown here. And essentially this is obtained from the soybean plant. There is also Silymarin, which comes from the milk thistle plant, which is shown here in this image, in this photograph. Silymarin is actually a mixture of a number of different compounds with three principal components consisting of silibinin, silidionin, and silicrystine. The most important one, the most efficacious one is actually silibinin, whose structure is shown at the bottom of this slide. We mentioned the phenolic acids that are used commonly in skincare. These are giving you the structure, or this slide gives you the structure of those. We have caffeic acid shown here on the left, rosmarinic acid on the right, and then ferulic acid in the middle on the bottom here. In addition to that, we have various other phenolic compounds. We already talked about BHT, or butyl hydroxytoluene. So this is, you already have seen that. Kojic acid, this is actually a skin whitening agent, but it has antioxidant properties as well. You can see it has a hydroxyl group here. Ellagic acid, this is also a skin whitening agent, but it also has hydroxyl groups which provide it with antioxidant properties. This is the structure for resveratrol. As you can see here, it has two phenyl rings and three pendant hydroxyl groups coming from that. And here we have the structure of quercetin, which we already mentioned. And you can see you have various hydroxyl groups coming off of that structure as well. And this is a flavonoid type compound. So that brings us to the end of this chapter. And if you'd like to read a little bit more in relation to what we covered, or even in any additional information about the treatment of skin with antioxidants, you can find that information in chapter 8. And hopefully you enjoyed this portion of the course dedicated to the antioxidants. Have a good day.